In early 2022, the James Webb Space Telescope opened its infrared eyes for the first time and peered deeper into the cosmos than humanity had ever seen before. Within weeks, astronomers were celebrating the stunning images of distant galaxies, nebulae, and cosmic structures that exceeded even their most optimistic expectations. But as the data kept rolling in and scientists began analyzing what Webb was actually showing them, celebration gradually turned to confusion, then to concern, and finally to something approaching scientific crisis. Because Webb wasn't just finding distant galaxies, it was finding galaxies that shouldn't exist. Galaxies that appeared to have formed so early in the universe's history that there simply wasn't enough time for them to be there. And the more Webb looked, the more impossible galaxies it found. To understand why this is such a profound problem, we need to start with what we thought we knew about how the universe makes galaxies in the first place. The story begins 13.8 billion years ago with the Big Bang. In the first fractions of a second, the universe was an impossibly hot, dense soup of fundamental particles and energy. As it expanded and cooled, protons and electrons formed, but the universe was still too hot for them to combine into atoms. For the first 380,000 years, the cosmos was opaque, filled with a fog of plasma that light couldn't penetrate. Then, when the temperature dropped enough, electrons and protons finally combined to form neutral hydrogen atoms. This moment is called recombination, and it's when the universe became transparent for the first time. The cosmic microwave background radiation we detect today is the afterglow of this event, light that's been traveling through space for 13.8 billion years. But recombination didn't create a perfectly smooth universe. There were tiny quantum fluctuations from the earliest moments of the Big Bang, minuscule variations in density from place to place. These tiny ripples would become the seeds of all cosmic structure. In regions that were even slightly denser than average, gravity began to pull matter together. Dark matter, which doesn't interact with light but does interact with gravity, started clumping first. These dark matter halos created gravitational wells that attracted ordinary matter, mostly hydrogen and helium gas left over from the Big Bang. As gas fell into these wells, it heated up through compression. But here's the crucial part. For a galaxy to form, that gas needs to cool down and condense. Hot gas has too much pressure and too much random motion to collapse into stars. The cooling process takes time. The gas radiates away its thermal energy, gradually becoming denser and cooler until regions of it can finally collapse under their own gravity. Only then can you begin forming stars, and you need a lot of stars, organized into a coherent structure before you can call it a galaxy. For decades, our models suggested this entire process, from the initial tiny ripples in density to the first recognizable galaxies, would take somewhere between 400 and 800 million years after the Big Bang. Some optimistic models pushed it slightly earlier, maybe to 300 million years, but that was considered aggressive. The reasoning was straightforward. You need time for dark matter to clump, time for gas to fall into those clumps, time for the gas to cool, time for stars to form, and time for enough stars to form that you have something that looks like a galaxy rather than just a loose cluster of stars. Every step in this process has a speed limit set by physics. Dark matter clumps at a rate determined by gravity and the expansion of the universe. Gas cools at a rate determined by atomic physics and the density of the gas. Stars form at a rate limited by how fast gas clouds can collapse. You can't skip these steps, and you can't make them go arbitrarily faster. So, when James Webb started finding galaxies at redshifts indicating they existed just 200 to 300 million years after the Big Bang, astronomers were surprised, but not immediately alarmed. These were right at the edge of what the most optimistic models predicted. Perhaps the universe was just a bit more efficient at making galaxies than we thought. But then Webb kept looking, and the galaxies kept getting earlier, and earlier, and earlier. Glass Z13 appeared to be a galaxy existing just 300 million years after the Big Bang. That was remarkable, but maybe explainable. Then came Sears 93316, which appeared even earlier, perhaps as early as 250 million years post-Big Bang. Astronomers started doing double takes. The follow-up observations to confirm these findings were prioritized. Because if these were real galaxies, and if they really were that old, then something in our understanding of galaxy formation was seriously wrong. The confirmation process is worth understanding, because it rules out the most obvious objection. What if these are just measurement errors? What if these aren't actually distant, ancient galaxies, but rather closer, more recent galaxies that just happen to look like distant ones? This is where spectroscopy comes in. When light travels through the expanding universe, its wavelength gets stretched. The faster the universe was expanding at the time the light was emitted, and the longer the light has been traveling, the more stretched it becomes. This stretching shifts the light toward redder wavelengths, an effect called redshift. By measuring exactly how much a galaxy's light has been redshifted, we can calculate how long that light has been traveling, and therefore how long ago it was emitted, and therefore how old the galaxy is. Early observations used photometry, which measures brightness in different wavelength bands. This can give you a rough estimate of redshift, but it's not precise. The real confirmation comes from spectroscopy, where you split the light into its component wavelengths and look for specific features like emission lines from hydrogen or other elements. These features have known wavelengths when emitted, so by measuring where they appear in the observed spectrum, you can calculate the redshift with high precision. Webb has confirmed multiple galaxies with spectroscopic redshifts greater than 10, meaning we're seeing them as they were less than 500 million years after the Big Bang. Some have redshifts greater than 12, pushing into the 300 to 350 million year range. And the list keeps growing. Every time Webb spends a few days staring at a patch of sky, it finds more. These aren't flukes or errors. These are real galaxies, confirmed by multiple independent observations using different techniques. The universe really did make galaxies this early. But how? Let's walk through the timeline problem in detail. At 200 million years after the Big Bang, the universe had only just begun to form its first stars. These would have been massive, short-lived stars made purely of hydrogen and helium, called population 3 stars. We've never actually observed one directly, which makes sense because they should have exploded as supernovae after just a few million years of life. Those supernovae would have seeded the surrounding gas with heavier elements, allowing the next generation of stars to form with a more complex chemistry. This second generation, called population 2 stars, would have been more stable and longer lived. But even optimistically, this process of first stars forming, exploding, and seeding a second generation takes at least 100 million years. So at 200 million years post-Big Bang, you might have some population 2 stars starting to form. You probably have some small clusters of stars here and there, loosely bound together. What you should not have is a fully formed galaxy with billions of stars organized into a coherent structure with rotation and defined morphology. Yet that's exactly what Webb is finding. These early galaxies aren't just a few stars loosely clustered together. They're genuine galaxies with structures, with clear signs of organized rotation, with populations of stars that include both young, hot, blue stars and older, cooler red stars. That implies multiple generations of star formation have already occurred. That implies these galaxies have been building up their stellar populations for a significant time before we observe them. If we're seeing them at 200 million years after the Big Bang, when did they start forming? At 100 million years? At 50 million years? That pushes us into an era when the universe should have barely had any stars at all, let alone organized galaxies. One proposed solution is that the very first stars formed earlier than we thought, and they formed much more efficiently than our models predict. Perhaps the initial conditions in some regions of the universe were just right for extremely rapid star formation. Perhaps there were pockets of unusually high density that allowed gas to cool faster. Perhaps some feedback mechanism we don't understand accelerated the process. But every time you try to make this work quantitatively, you run into problems. To get a billion-star galaxy at 200 million years post-Big Bang, you need to start forming stars by, at the latest, 100 million years post-Big Bang. That means gas needs to have cooled and collapsed by that time, which means dark matter halos needed to have formed and grown substantial enough to trap that gas even earlier, perhaps by 50 million years post-Big Bang. But dark matter halo growth is limited by gravity and the expansion rate of the universe, which we understand very well thanks to cosmic microwave background measurements. There's only so fast halos can grow, and it's not fast enough to support what we're seeing. You can try to tweak the initial density fluctuations, making them slightly larger than the cosmic microwave background suggests. But if you make them too much larger, you run into other problems. You'd see effects on the cosmic microwave background itself that we don't observe. You'd predict far more structure formation than we actually see in the later universe. Every solution creates new problems. Another approach is to propose that star formation in the early universe was far more efficient than it is today. In the modern universe, when a gas cloud collapses to form stars, only a small fraction of the gas actually ends up in stars. Maybe 1 to 5% efficiency is typical. The rest of the gas is heated and blown away by stellar winds and supernova explosions, or remains as diffuse gas between the stars. But what if, in the very early universe before those first supernovae, star formation was much more efficient? What if 30 or 40% of the gas ended up in stars? That would speed things up considerably. The problem is, we have no good physical reason to expect this. In fact, most models suggest star formation should be less efficient in the early universe, not more. The gas is hotter, more turbulent, and lacks the heavy elements that help gas clouds cool and fragment into stars. Without elements like carbon and oxygen, there are fewer ways for gas to radiate away its thermal energy. It should be harder to form stars in the early universe, not easier. Yet, somehow, the universe managed to build galaxies faster than our models say is possible. And, as we're about to see, it's not just about timing. Some of these early galaxies aren't just too early, they're also too massive, too bright, too organized, and too mature. They're not just breaking the timeline. They're breaking multiple rules simultaneously. As more data accumulated throughout 2022 and into 2023, astronomers began noticing something even more disturbing than the age problem. Some of these early galaxies weren't just unexpectedly present, they were unexpectedly huge. They had stellar masses that shouldn't exist at their cosmic epoch, no matter how efficient you made the star formation process. The universe had apparently found a way to build not just galaxies earlier than expected, but to build massive galaxies earlier than seemed physically possible. And that's when the crisis in cosmology really began. The galaxy designated GNZ11 held the record for most distant known galaxy for several years before Webb launched. Discovered by the Hubble Space Telescope, it sits at a redshift of 10.6, meaning we're seeing it as it existed roughly 400 million years after the Big Bang. When astronomers first analyzed GNZ11, they were struck by how bright it appeared. This wasn't some faint smudge barely visible at the limits of Hubble's capabilities. This was a galaxy shining with the luminosity of 25 billion suns, despite being observed at a time when the universe was only 3% of its current age. To put that in perspective, our Milky Way galaxy contains somewhere between 200 and 400 billion stars. GNZ11 was estimated to contain about 1 billion stars. That might sound like less, but remember the timescale. The Milky Way has had 13.6 billion years to accumulate its stellar population. GNZ11 had maybe 300 million years, possibly less. If you do the math on the star formation rate required to build a billion-star galaxy in 300 million years, you get a number that's uncomfortably high. You'd need to be forming stars at a rate of about 3 to 4 solar masses per year, sustained over that entire period. For comparison, the Milky Way today forms roughly 1 to 2 solar masses worth of new stars per year, and we have a much larger reservoir of gas to work with. But here's where it gets worse. Stars don't live forever, especially not the hot, massive stars that dominate early star formation. A massive star might live for only a few million years before exploding as a supernova. Medium-sized stars live longer, and small red dwarfs can live for trillions of years. But in the early universe, you expect the stellar population to be skewed toward larger, shorter-lived stars. That means GNZ11 isn't just forming new stars. It's replacing stars that have already lived and died. The actual total star formation over the galaxy's lifetime needs to be significantly higher than the 1 billion stars we observe, because many stars have already completed their life cycles. When you factor in stellar death, the required star formation rate climbs even higher, perhaps to 5 or 6 solar masses per year. Now, you might think, okay, that's high, but maybe possible. Perhaps this galaxy just had an unusually large reservoir of gas to work with. Perhaps it formed in an especially dense region of the universe where there was more material available. But that explanation runs into the problem of where that material comes from. In the early universe, the density of ordinary matter was set by Big Bang nucleosynthesis. You have a certain amount of hydrogen and helium per unit volume, and that's determined by the physics of the first few minutes after the Big Bang. You can't just arbitrarily increase it. Dark matter provides the gravitational scaffolding, but dark matter doesn't turn into stars. You need ordinary baryonic matter, and there's only so much of it in any given region of space. To accumulate enough gas to build GNZ11, you need a dark matter halo of a certain minimum mass. That halo needs to grow through gravitational attraction, pulling in more dark matter and ordinary matter from its surroundings. But halo growth rates are limited by the expansion of the universe and by the distance from which you can pull material. In the early universe, distances are smaller, which should help, but the expansion rate is also faster, which works against you. When cosmologists ran simulations of structure formation using our standard cosmological model, called Lambda-CDM, they found that halos massive enough to host a galaxy like GNZ11 should be extremely rare at that epoch. Not impossible, but rare. Finding one wasn't necessarily a crisis, but GNZ11 wasn't alone. As Webb continued its observations, it found more galaxies at similar redshifts with similar masses. Sears 93316, Glass Z12, Jade's GS30. The list kept growing. Each one was a galaxy that stretched the limits of what Lambda-CDM predicted should exist at that time. And then, Webb found JWST. This galaxy, observed at a redshift of approximately 14.3, exists as we see it roughly 280 million years after the Big Bang. Initial analysis suggests it contains approximately 500 million solar masses worth of stars, possibly more depending on the assumed stellar population characteristics. It's extremely bright, implying vigorous ongoing star formation, and it shows evidence of chemical enrichment, meaning multiple generations of stars have already lived and died, producing heavier elements that have been incorporated into the next generation of stars. Let's pause and think about what has to happen for this galaxy to exist. First, dark matter halos have to form and grow large enough to trap significant amounts of gas. This requires the initial density fluctuations to grow through gravitational instability, a process that takes time. Second, gas has to fall into these halos and cool down enough to form stars. Cooling time depends on density and composition, but it's not instantaneous. Third, the first generation of stars has to form, live out their short lives, and explode as supernovae, enriching the surrounding gas with heavy elements. Fourth, a second generation of stars, enriched with those heavy elements, has to form. Fifth, this process has to repeat enough times to build up a population of 500 million stars organized into a coherent galaxy structure. And all of this has to happen in less than 280 million years. To make this timeline work, each step has to proceed at nearly maximum efficiency with minimal delays. The dark matter halo has to grow as fast as gravity allows. The gas has to cool as fast as atomic physics permits. Stars have to form at the highest rates sustainable. Supernovae have to enrich the gas immediately. The next generation of stars has to begin forming without delay. Every step has to work perfectly, and even then, you're pushing against the limits of what's physically possible. But the universe doesn't care about our limits. It made JWST GS0 somehow. The question is how? One proposal involves population 3 stars, those first-generation stars made of pure hydrogen and helium. If these stars were extremely massive, perhaps 100 or even 300 solar masses each, they would live very short lives, perhaps just 1 or 2 million years, and then explode as incredibly energetic supernovae called pair instability supernovae. These explosions would completely destroy the star, leaving no remnant, but they would enrich a huge volume of surrounding gas with heavy elements. If you had a population of these supermassive population 3 stars forming and exploding in rapid succession, you could potentially enrich enough gas quickly enough to jumpstart rapid galaxy formation. The problem with this scenario is that we have no direct evidence these supermassive population 3 stars actually existed. They're theoretically possible, but whether the early universe actually made them is unknown. Moreover, even if they did exist, the total mass of material they could process is limited. A 200 solar mass star that explodes and enriches the surrounding gas has only processed 200 solar masses worth of material. To build a galaxy with 500 million solar masses, you'd need millions of these stars forming and exploding. And that brings you back to the same timeline problem you were trying to solve in the first place. Another proposal involves primordial black holes. If black holes with masses of thousands or even millions of solar masses somehow formed in the very early universe, perhaps through direct collapse of gas clouds rather than through stellar death, these black holes could serve as seeds for galaxy formation. Material falling onto these black holes would release tremendous amounts of energy, heating and stirring the surrounding gas. Paradoxically, this heating might actually help galaxy formation by driving turbulence that causes gas to fragment into dense clumps that can collapse into stars. But primordial black holes are speculative. We have some theoretical models for how they might form, but no direct evidence they exist in significant numbers. And if they do exist, they would contribute to the overall dark matter density, which we've measured quite precisely through cosmic microwave background observations. You can't add a significant population of primordial black holes without throwing off other cosmological measurements. A more radical idea is that star formation in the early universe was just fundamentally different from what we see today. Perhaps in the dense, metal-poor conditions of the earliest galaxies, gas clouds could collapse more efficiently than our models predict. Perhaps stellar feedback, the process by which energy from stars and supernovae heats gas and prevents further star formation, was less effective in the early universe. Perhaps the initial mass function, the distribution of stellar masses when a population of stars forms, was weighted more heavily toward massive stars that live and die quickly, processing material faster. Each of these possibilities has some theoretical support, but also significant uncertainties. The physics of star formation is complex even in the local universe where we can observe it in detail. Extrapolating to the early universe, where conditions were dramatically different, and where we have no direct observations of the star-forming process, requires making assumptions that may or may not be valid. What's become increasingly clear as Webb data accumulates is that whatever process was building galaxies in the early universe, it was remarkably efficient. Perhaps too efficient. When you look at galaxies from later epochs, from 1 billion years post-Big Bang onward, their properties generally match what Lambda-CDM predicts. Galaxy masses, star formation rates, clustering properties, all of it fits the models reasonably well. But in that earliest period, from 200 to 500 million years post-Big Bang, something different was happening. The universe was churning out massive galaxies at a rate that seems to exceed what should be possible given the available time and material. And it's not just one or two exceptional cases. As Webb's survey programs continue and more data is analyzed, the number of these massive early galaxies keeps growing. Initial estimates suggested that perhaps 5 to 10 times more massive galaxies exist at high redshift than Lambda-CDM predicts. More recent analyses have suggested the discrepancy might be even larger, perhaps a factor of 20 or more for the most massive galaxies at the highest redshifts. If this holds up with continued observations and refined analysis, it represents a serious challenge to our cosmological model. You can't just tweak a few parameters to make this work. You'd need to change something fundamental about how structure forms in the early universe. Some cosmologists have proposed modifications to Lambda-CDM that add extra physics in the early universe. One popular idea is early dark energy. a hypothetical energy field that affected the expansion rate in the first billion years after the Big Bang, but then faded away. This would alter the timeline of structure formation in exactly the period where we're seeing discrepancies. Early dark energy models can be tuned to allow faster halo growth and earlier galaxy formation. But these models are ad hoc, added specifically to solve this problem rather than being motivated by independent physics. They also tend to create tensions with other cosmological observations, like the cosmic microwave background power spectrum. You fix one problem, but potentially create others. Another approach is to question whether our distance measurements might be systematically wrong. What if some of these high redshift galaxies aren't actually as distant as we think? What if there's some effect that's mimicking high redshift when the galaxy is actually closer and more recent? This is a hard sell because spectroscopic redshifts are quite reliable. We're measuring the wavelength shift of known atomic transitions like hydrogen-Lyman alpha emission. For the redshift measurement to be wrong, either our understanding of atomic physics would have to be wrong, or the expansion history of the universe would have to be dramatically different from what we measure through multiple independent methods. Neither seems likely. The more astronomers grapple with this problem, the more it seems like we're missing something fundamental. Either galaxy formation physics in the early universe operated in ways we don't understand, or cosmological structure formation happened faster than Lambda-CDM predicts, or some combination of both. The galaxies exist, that's not in question. Webb is seeing them. Multiple independent teams are confirming them. The data is solid. The universe made these galaxies somehow. Our models say it shouldn't have been able to. One of those things has to give. While astronomers were grappling with galaxies that appeared too early and too massive, another category of impossible galaxies had been quietly accumulating in the observational record for decades. These were galaxies that seemed to be spinning the wrong way. To understand why this is a problem, we need to talk about angular momentum and the cosmic web. When the universe was very young, shortly after the Big Bang, quantum fluctuations created tiny variations in density from place to place. As the universe expanded and evolved, these fluctuations grew through gravitational instability into the large-scale structure we see today. Dark matter and ordinary matter clumped together into an intricate network called the cosmic web, a vast interconnected structure of filaments, walls, sheets, and voids that spans the entire observable universe. Galaxies form at the intersections and along the filaments of this web, where matter is most concentrated. But the cosmic web doesn't just tell galaxies where to form, it also tells them how to spin. As matter flows along the filaments toward the regions where galaxies will form, it carries angular momentum. This is a consequence of tidal torque theory, which describes how gravitational interactions between different regions of the cosmic web impart rotation to collapsing structures. The theory makes a clear prediction. A galaxy's spin axis should be preferentially aligned perpendicular to the filament along which matter flowed to build it. In other words, if matter is flowing toward a forming galaxy primarily from the north and south along a cosmic filament, the galaxy should spin with its rotation axis pointing roughly north-south and its disk oriented east-west. This isn't a vague suggestion. It's a quantitative prediction that comes out of the mathematics of structure formation. For decades, this prediction seemed to hold up reasonably well. Surveys of galaxy orientations showed statistical correlations with the large-scale structure around them, roughly consistent with tidal torque theory. But as surveys became larger and more precise, cracks started to appear. Some galaxies had rotation axes that were aligned parallel to their filaments rather than perpendicular. Some seemed to have no correlation at all with the surrounding structure, and some galaxies appeared to be rotating in a direction that was completely opposite to what the inflow of matter from the cosmic web would predict. NGC 4622 is one of the most famous examples. It's a spiral galaxy located about 200 million light-years away in the constellation Centaurus. When astronomers first studied its rotation using spectroscopy, measuring the Doppler shift of light from different parts of the galaxy to determine which parts were moving toward us and which away, they found something bizarre. The galaxy's spiral arms were leading rather than trailing. In a normal spiral galaxy, the arms trail behind the direction of rotation, like water spiraling down a drain or cream stirring into coffee. You can think of it like this. As the galaxy rotates, stars and gas get stretched out into spiral patterns, and these patterns naturally trail behind the rotation. But in NGC 4622, detailed analysis showed that the outer spiral arms were actually leading the rotation. It was as if the galaxy was spinning backwards relative to its own structure. Further observations revealed that NGC 4622 actually has two sets of spiral arms rotating in opposite directions. The inner arms are trailing as expected, but the outer arms are leading. This suggests the galaxy's outer regions are rotating opposite to its inner regions, or that the spiral arm pattern itself is somehow rotating independently of the stars and gas. Neither interpretation fits comfortably with our understanding of galaxy dynamics. Mergers can potentially explain some wrong-way rotations. If two galaxies collide and merge, and they happened to be rotating in opposite directions before the merger, the resulting galaxy might end up with complex rotation patterns. Material from one galaxy might be rotating one way, while material from the other rotates the opposite way. Over time, these counter-rotating components should mix and settle down into a single coherent rotation. But during the transition period, you might observe apparently backwards rotation in parts of the galaxy. The problem is that NGC 4622 doesn't show obvious signs of a recent major merger. It's not disturbed or asymmetric in the way you'd expect from a recent collision. Its structure is relatively regular and organized. If a merger did cause its strange rotation pattern, it must have happened long enough ago that the galaxy has settled back into an orderly appearance, but recently enough that the counter-rotating components haven't fully mixed. That's a narrow window, and while it's possible, it seems like special pleading when you're trying to explain one specific galaxy. But NGC 4622 isn't alone. As surveys have cataloged the rotation properties of thousands of galaxies, a significant fraction show anomalous rotation properties. Some surveys have found that 10 to 20% of spiral galaxies have misaligned rotation, where the direction of spin doesn't match what you'd predict from the surrounding large-scale structure. That's far too many to explain away as rare merger events. If 1 in 5 or 1 in 10 galaxies is rotating the wrong way, something systematic is going on. There are also galaxies with counter-rotating cores, where the central region of the galaxy rotates in the opposite direction from the outer disk. NGC 4550 is a spectacular example. It's a lenticular galaxy where approximately half the stars are orbiting clockwise and the other half are orbiting counterclockwise, as if two galaxies were merged together but forgot to settle on a common direction. The stars in both populations are thoroughly mixed spatially. You can't point to one region and say, "Those stars are rotating this way." Instead, at every location in the galaxy. About half the stars are going one way, and half are going the other way. They're all occupying the same space, just moving in opposite directions. This is thought to be the result of a merger, where the two progenitor galaxies had oppositely directed angular momentum, and after the merger, the stars from each progenitor retained their original orbital directions. But here's the puzzle. Why would two galaxies that happened to be near each other in space, both forming from the same large-scale structure in the cosmic web, have opposite angular momentum in the first place? According to tidal torque theory, their spins should be correlated, not anti-correlated. If they both formed from matter flowing along the same filaments, they should be spinning in the same direction, or at least in related directions. To get opposite spins, you need either random chance, which should be rare, or some physical mechanism that preferentially creates counter-rotating pairs. No such mechanism is known. Polar ring galaxies add another layer of strangeness. These are galaxies where the main stellar disk is surrounded by a ring of stars, gas and dust, orbiting in a plane roughly perpendicular to the disk. NGC 46520A is the classic example, with a prominent ring that appears to be stably orbiting at a right angle to the main galaxy. The ring isn't some temporary debris from a recent collision. It's rotating coherently, has been stable for hundreds of millions of years, and contains both old stars and active star formation. The standard explanation is that a polar ring forms when a galaxy accretes material from a companion galaxy or from the intergalactic medium, and that material happens to have angular momentum perpendicular to the existing disk. Over time, this material settles into a stable ring orbit. But again, why would infalling material have perpendicular angular momentum? If everything is forming from the same cosmic web structure, angular momentum vectors should be correlated, not randomly oriented. Yet, polar ring galaxies, while rare, are not vanishingly rare. Catalogs contain dozens of confirmed examples and hundreds of candidates. That's enough to suggest there's some aspect of galaxy formation and evolution we're not fully capturing. The statistical studies of galaxy alignments paint an even more confusing picture. Large surveys have measured the orientations of hundreds of thousands of galaxies and compared them to maps of the cosmic web reconstructed from galaxy positions. The correlations are there, but they're weaker than theory predicts. Galaxies do show some tendency to align their spins perpendicular to filaments, but the effect is subtle and varies depending on galaxy mass, environment, and redshift in ways that don't always match predictions. Some studies have even found evidence that galaxies in certain mass ranges preferentially align parallel to filaments rather than perpendicular, exactly opposite to the standard prediction. Other studies find no significant correlation at all for certain galaxy populations. The results are inconsistent between different surveys and different analysis methods, which suggests we might be dealing with systematic uncertainties in how we measure galaxy orientations, or how we reconstruct the cosmic web. But even accounting for uncertainties, the picture is messier than it should be. One possibility is that galaxy mergers and interactions are more common and more influential than we've appreciated. Every time two galaxies merge, their angular momentum vectors combine in complex ways. If galaxies have undergone multiple mergers over their lifetimes, each one potentially reorienting the spin, then the connection between a galaxy's current spin and the initial angular momentum it acquired from the cosmic web might be thoroughly scrambled. The galaxy's spin today would be determined more by its merger history than by its initial conditions. But this explanation has problems. In dense environments like galaxy clusters where mergers are frequent, you might expect spins to be completely randomized. Yet, observations show that even cluster galaxies retain some correlation with large-scale structure. Conversely, in low-density environments where mergers should be rare, you still find a substantial fraction of galaxies with apparently anomalous spins. The relationship between merger rate and spin alignment doesn't quite work out. Another possibility is that tidal torque theory, while capturing the essential physics, oversimplifies the complexity of real galaxy formation. The theory tends to assume a smooth inflow of matter along well-defined filaments, but the real universe is lumpier and more chaotic. Matter doesn't flow in smoothly. It clumps into smaller dark matter halos that then merge together. Each of these halos brings its own angular momentum, acquired from slightly different parts of the cosmic web. When they merge, their angular momenta combine vectorially, and the resulting total angular momentum might point in a direction that seems anomalous relative to the large-scale filament structure. Simulations that include this lumpy, hierarchical assembly process do show more scatter in the spin-filament alignment than the simple theory predicts. Some simulated galaxies end up with spins that are misaligned or even anti-aligned with their filaments. But the simulations still don't produce as much misalignment as observations suggest, and the discrepancies tend to be worse for massive galaxies than for smaller ones, which is the opposite of what you'd expect if lumpy assembly were the main culprit. There's also the question of galaxy satellites. Most large galaxies, including our own Milky Way, are surrounded by a population of smaller satellite galaxies. These satellites orbit the larger galaxy in various directions, and in principle, those directions should be related to the cosmic web structure. But observations of the Milky Way's satellites have revealed something strange. Instead of being randomly distributed in a roughly spherical cloud around the galaxy, as you'd expect, the satellites are arranged in a thin, disk-like distribution. The satellites orbit the Milky Way preferentially in one plane, almost like planets orbiting the Sun. The Andromeda Galaxy, our nearest large neighbor, shows the same pattern. Its satellites are arranged in a thin plane rather than a spherical distribution. This is sometimes called the satellite plane problem, and it's proven remarkably difficult to explain. In simulations of galaxy formation using standard dark matter models, satellite galaxies end up distributed more or less spherically around their hosts. You can get some flattening, especially if the host galaxy's dark matter halo is itself flattened, but getting the extreme thinness observed in the Milky Way and Andromeda satellite distributions is very hard. Some simulations have managed it, but they require special conditions or careful selection of which simulated galaxies you compare to real ones. The satellite plane problem connects to the wrong-way galaxy problem because both involve angular momentum in unexpected configurations. The satellite plane suggests that when the Milky Way was forming and accreting smaller galaxies, those smaller galaxies were all coming in from similar directions with correlated angular momenta. That could happen if they were all falling in along the same cosmic filament. But if that's the case, why do some satellite systems show the opposite pattern? Why do some large galaxies have satellites rotating in the opposite direction from the main galaxy's spin? The more you look at galaxy rotation, the more the picture fragments into special cases and exceptions. For every rule, there's a substantial population of galaxies breaking it. Some of this is surely due to the messy, chaotic process of galaxy formation and evolution. Galaxies collide, merge, get tidally stripped, accrete gas from the intergalactic medium, and undergo bursts of star formation that drive gas outflows. All of these processes can alter a galaxy's angular momentum. After 10 billion years of this chaos, maybe it's not surprising that many galaxies have the spins that don't obviously relate to their current environment. But that's a somewhat defeatist position. It amounts to saying that galaxy spins are too complicated to predict, that we should give up on connecting them to the underlying cosmic web structure. And that's troubling, because angular momentum is fundamental. It's one of the most conserved quantities in physics. If we can't predict or explain something as basic as which way a galaxy spins, what can we predict? The answer might be that we're missing some important physical process. Perhaps magnetic fields play a larger role than we've appreciated. The cosmic web isn't just made of matter and dark matter. It also contains magnetic fields, and those fields can exert torques on gas as it flows through the web. Perhaps in some circumstances, magnetic torques can flip or reorient a galaxy's spin, or perhaps feedback from supermassive black holes, which are now known to reside at the centers of most large galaxies, can affect angular momentum in ways we haven't fully modeled. When a black hole accretes matter and launches powerful jets, those jets carry energy and angular momentum out of the galaxy. Over millions of years, this could potentially alter the galaxy's net spin. These are speculative ideas that haven't been fully developed or tested. But the observations are clear. A substantial fraction of galaxies are rotating in ways that don't fit neatly with our theoretical expectations. They're not impossibly impossible in the way that a galaxy existing before the Big Bang would be impossible, but they're uncomfortably improbable. They suggest that our understanding of how galaxies acquire and retain angular momentum is incomplete. And, as we're about to see, it's not just about how galaxies spin, it's also about where they spin. If you look at a map of the universe on the largest scales, you'll see the cosmic web in all its glory. Filaments of galaxies stretching across hundreds of millions of light years, connecting massive clusters where thousands of galaxies congregate. Between these filaments are voids, vast empty regions that contain very few galaxies. These voids aren't completely empty, but they're severely underdense compared to the filaments and clusters. A typical cosmic void might be 100 to 300 million light-years across and contain perhaps 10% of the average matter density of the universe. Some voids are even emptier, containing just a few percent of average density. The existence of voids is a natural consequence of structure formation. In regions that started out slightly less dense than average, gravity had less material to work with. While overdense regions collapsed and formed galaxies, underdense regions became even more underdense as matter drained out of them, flowing toward the surrounding filaments and clusters. Over billions of years, voids expanded as the universe expanded, becoming ever more empty. Today, they represent about 40% of the universe's volume but contain only a small fraction of its galaxies. The physics of void formation is well understood, and the voids we observe match theoretical predictions quite well. Their sizes, shapes, and degree of emptiness all fit with structure formation models. But there's a problem. Some voids contain galaxies they shouldn't have. Galaxies that are too large, too bright, or too well formed to have assembled in such an underdense environment. These void galaxies are forcing astronomers to reconsider what they thought they understood about where galaxies can form. MCG 01, 02, 05 is one of the most striking examples. It's a spiral galaxy located in the middle of an enormous void, surrounded by virtually nothing. The nearest substantial galaxy concentration is more than 100 million light-years away. This galaxy is sitting in a region where the density of dark matter and ordinary matter is perhaps 5% of the cosmic average. And yet, MCG Poiso 10201 Feme is not some dim, stunted dwarf galaxy barely clinging to existence. It's a reasonably large spiral with active star formation, organized structure, and a mass of several billion solar masses. How did it get there? To form a galaxy, you need a dark matter halo massive enough to trap and hold on to gas. In the standard picture of structure formation, halos grow through gravitational collapse. Regions that are slightly overdense attract more matter, becoming progressively denser, until eventually they collapse into bound structures. But in a void, you don't have overdense regions. By definition, a void is underdense. The very reason voids exist is that matter has drained out of them. Any small density fluctuations that might have seeded galaxy formation in a void would be too weak to overcome the void's expansion. As the void grows and empties out, any proto-halos within it should be disrupted and absorbed into the surrounding filaments. This doesn't mean voids should be completely empty of galaxies. Small dwarf galaxies can exist in voids, formed in the few small halos that manage to hold together. Observations confirm that voids do contain populations of dwarf galaxies, though even these are less common than in higher density regions. But large galaxies like MCG Poiso 10201 should be exceedingly rare in voids if they exist at all. Yet surveys have found dozens of them. The Boötes void, one of the largest known voids, was discovered in the 1980s and initially thought to be completely empty. Follow-up surveys found approximately 60 galaxies within it, far fewer than the 2,000 you'd expect in a similar volume of average density space. Most of these 60 galaxies are small and dim, consistent with void expectations. But a handful are substantial galaxies that have no obvious reason to exist there. One proposal is that void galaxies formed before the void became a void. In the very early universe, before structure had significantly evolved, density contrasts were small. A region that would eventually become a void was only slightly less dense than average, not dramatically underdense like it is today. Perhaps in that early period, some galaxy-seeding dark matter halos managed to form and begin accumulating gas. Then, as the universe evolved and the surrounding matter drained away into filaments, these nascent galaxies found themselves increasingly isolated. But they had already gotten started, and the gas they'd already accumulated was bound tightly enough to their dark matter halos that it couldn't escape. So they continued forming stars and evolving into galaxies, even as the void grew around them. This scenario can work for small void galaxies, but it struggles to explain large ones. A large galaxy requires a massive dark matter halo, and massive halos grow primarily through mergers with other halos. But in a void, there are no other halos nearby to merge with. The void galaxy should remain small, unable to grow beyond its initial seed mass. Yet some void galaxies are demonstrably large and massive, implying substantial growth over time. Where did the material for that growth come from? Another idea is that void galaxies formed at the edges of the void and then migrated inward. Galaxies aren't stationary. They have velocities relative to the expansion of the universe, called peculiar velocities, that cause them to move through space. A galaxy that formed in a filament at the edge of a void might have a peculiar velocity pointing into the void, causing it to drift inward over billions of years. This could explain why we find some substantial galaxies in void interiors. They didn't form there. They moved there. But peculiar velocities are typically a few hundred kilometers per second, and voids are hundreds of millions of light years across. Even over billions of years, a galaxy moving at a few hundred kilometers per second wouldn't penetrate very far into a large void. This mechanism might explain galaxies in the outer regions of voids, but it has trouble explaining galaxies in void centers. There's also a more radical possibility. What if our understanding of structure formation in low-density environments is incomplete? Most simulations and theoretical models focus on average and high-density regions because that's where most galaxies are. Voids are treated as relatively uninteresting, the places where galaxy formation simply didn't happen. But perhaps there are physical processes specific to voids that we haven't properly accounted for. For instance, voids are expanding faster than the average expansion rate of the universe. This is because they're underdense, so there's less gravity slowing down their expansion. Could this rapid expansion create unusual conditions for galaxy formation? Perhaps gas dynamics in an expanding void behave differently than in a collapsing overdensity, allowing gas to cool and form stars in ways we haven't modeled. This is speculative, and there's no concrete evidence for it, but the existence of unexplained void galaxies suggests we might be missing something. While void galaxies represent an environment where galaxies shouldn't form, there's an opposite problem. Environments where galaxies are packed too closely together. Compact galaxy groups consist of multiple galaxies in a very small volume of space, moving at high relative velocities, and yet somehow remaining bound together for hundreds of millions or even billions of years. They shouldn't be stable. Either they should merge together into a single large galaxy, or the high velocities should cause them to fly apart. Yet they persist. Stephan's quintet is perhaps the most famous example. It consists of 5 galaxies in the constellation Pegasus, located about 280 million light-years away. 4 of the 5 galaxies are genuinely close together in space, while the 5th is actually much closer to us and just happens to appear near the others from our perspective. The 4 interacting galaxies occupy a region of space only about 200,000 light-years across. For context, the Milky Way itself is about 100,000 light-years in diameter, so you could fit all 4 galaxies into a volume not much larger than 2 Milky Ways. But these galaxies aren't small. They're full-sized galaxies, each with masses comparable to or exceeding the Milky Way, and they're not moving slowly. Spectroscopy reveals relative velocities of about 1,000 kilometers per second between some group members. At those speeds, you'd expect the galaxies to either collide and merge within a few hundred million years, or achieve enough velocity to escape each other's gravitational pull and fly apart. Yet Stephan's quintet has been together for at least 1 billion years, possibly longer. Observations show evidence of past interactions between group members. There are tidal tails of stars stripped from galaxies, shock waves in the gas between galaxies, and active star formation triggered by the interactions. But somehow, the group hasn't completed its merger. The galaxies are dancing around each other, interacting but not quite colliding, existing in a state that seems dynamically unstable but has persisted for cosmologically significant timescales. The standard explanation involves dark matter. Each galaxy is embedded in a dark matter halo much larger than the visible galaxy. When the galaxies appear to pass close to each other, their dark matter halos might actually still be separated, preventing direct collision. The gravitational interactions between the halos can transfer energy and angular momentum in complex ways, potentially stabilizing the system longer than you'd expect from looking at just the visible galaxies. Simulations that include dark matter halos can produce long-lived compact groups under certain conditions. But those conditions are fairly specific. You need the halos to have the right masses, the right density profiles, the right initial velocities, and the right orbital configurations. If any of these parameters are off, the system either merges quickly or flies apart. The fact that we observe many compact groups suggests either we're catching them at a special moment in their evolution, right before they merge or disperse, or there's something about how they form that naturally produces these quasi-stable configurations more often than we'd expect from random chance. Another puzzle is why compact groups exist preferentially in certain environments. You might expect them to form primarily in high-density regions like galaxy clusters, where galaxies are numerous and interactions are common. But many compact groups are found in relatively isolated regions, far from major clusters. They appear to be distinct structures, not just dense knots within larger structures. This suggests they formed through a specific process, perhaps related to the filaments of the cosmic web, but the details remain unclear. Adding to the strangeness, there's the satellite plane problem I mentioned earlier. The Milky Way is surrounded by dozens of small satellite galaxies, and these satellites are not randomly distributed around us. Instead, they were arranged in a thin, disk-like structure. At least half of the Milky Way's satellites orbit within a plane that's only about 30,000 light-years thick, but extends more than 1,000,000 light-years across. This plane is inclined at a steep angle to the Milky Way's main disk, so it's not just satellites sitting in our galactic disk. It's a separate structure. The Andromeda Galaxy shows the same phenomenon. Its satellites are also arranged in a thin plane, again inclined to Andromeda's main disk. The plane of Andromeda's satellites is actually roughly aligned with the plane of the Milky Way's satellites, despite the two galaxies being separated by 2.5 million light-years. This alignment might be coincidental, or it might be telling us something about how both galaxies formed from the same large-scale structure in the cosmic web. In standard cold dark matter models, satellites should be distributed more or less isotropically around their host galaxy. They form from dark matter subhalos that fall into the host halo from various directions, and there's no preferred plane. Simulations consistently produce roughly spherical distributions of satellites, not thin disks. You can get some flattening if the host halo itself is flattened, and you can preferentially destroy satellites that pass too close to the host galaxy, which can create some asymmetry. But producing the extreme thinness observed in the Milky Way and Andromeda satellite planes is very difficult. Some simulations have managed it by carefully selecting initial conditions, or by following only certain types of halos, but there's no consensus on whether these represent typical outcomes or specially contrived cases. One controversial explanation is that the satellite planes are tidal dwarf galaxies, formed from material stripped during past galaxy mergers, rather than genuine satellites that formed independently. If the Milky Way or Andromeda underwent a major merger in the past, tidal tails of material could have been pulled out of the merging galaxies. These tails would naturally lie in a plane related to the orbital plane of the merger. If the material in these tails subsequently fragmented and formed small galaxies, those galaxies would retain the planar distribution. This scenario has some support from simulations showing that tidal dwarf galaxies can indeed form in merger tails and survive for billions of years. but it requires the Milky Way and Andromeda to have undergone major mergers relatively recently, within the last few billion years, and there's limited evidence for such recent mergers. The Milky Way shows signs of having accreted several smaller galaxies over its history, including the Sagittarius dwarf, which is currently being torn apart. But these are minor mergers that wouldn't produce the observed satellite plane. A major merger involving a galaxy, a significant fraction of the Milky Way's mass, should have left more obvious scars in the structure and kinematics of our galaxy's stars. Another piece of the location puzzle involves what are called ultra-diffuse galaxies. These are galaxies with sizes comparable to the Milky Way, but with far fewer stars, sometimes 100 times fewer. They're so dim and spread out that they were largely overlooked until recent surveys with sensitive telescopes revealed them in large numbers. Many ultra-diffuse galaxies are found in galaxy clusters, which is strange because clusters are harsh environments. The hot gas pervading a cluster, the tidal forces from the cluster's gravitational field, and the high-speed encounters with other galaxies all tend to disrupt and destroy fragile galaxies. Yet ultra-diffuse galaxies, which are very fragile due to their low densities, somehow survive in clusters. Some of them have been in clusters for billions of years, long enough that they should have been torn apart. But they're still there, intact and identifiable. One possibility is that ultra-diffuse galaxies have much more dark matter than their visible properties suggest. If they're embedded in dark matter halos far more massive than their stellar content would imply, those halos could protect them from the cluster environment. The stars would be sparse and spread out, but the dark matter would hold everything together. Observations of some ultra-diffuse galaxies support this idea, showing that their internal dynamics require large amounts of dark matter. But other ultra-diffuse galaxies appear to have normal or even low amounts of dark matter, which brings us back to the question of how they survive. There's also the question of how they formed in the first place. Why would some galaxies end up large and diffuse while others are compact? Is it related to the environment where they formed? To the timing of their formation? To their merger history? Current models don't provide a clear answer. We can make ultra-diffuse galaxies in simulations under certain conditions, but we can also not make them under slightly different conditions. There's no robust prediction that says ultra-diffuse galaxies should exist in the numbers we observe. All of these location-based puzzles, from void galaxies to compact groups to satellite planes to ultra-diffuse galaxies, point to the same underlying issue. Where a galaxy forms and where it ends up matter enormously for its properties and evolution. The environment sculpts the galaxy. But our understanding of this environmental dependence is incomplete. We can explain some cases with some effort, but there are always exceptions, always galaxies in places they shouldn't be, with properties that don't quite fit. The universe makes galaxies in voids where there's not enough material. It crams galaxies together in compact groups that should merge or disperse. It arranges satellite galaxies in planes when they should be spherically distributed. It preserves fragile galaxies in harsh cluster environments where they should be destroyed. For every rule we formulate about where galaxies can exist and how their location affects them, the universe provides counterexamples. And this brings us to the uncomfortable conclusion that either galaxies are far more adaptable and resilient than we give them credit for, able to form and survive in a wider range of environments than our models predict, or there are aspects of galaxy formation and evolution that we're fundamentally misunderstanding. The cosmic web tells galaxies where to form, but galaxies don't always listen. They show up in the wrong places, spin the wrong ways, and persist in environments that should destroy them. Each individual case can potentially be explained with some additional physics or some special circumstances. But when you step back and look at the full picture, the accumulation of exceptions and anomalies starts to feel like more than just noise. It feels like a signal we're not quite interpreting correctly. So here we are, confronted with galaxies that appear too early in cosmic history. Galaxies that grow too massive too quickly. Galaxies spinning in directions that don't align with the cosmic web that created them. And galaxies existing in places where they have no business being. Each category of impossible galaxy could potentially be explained away with some additional physics, some tweaked parameters, or some appeal to rare but possible circumstances. But when you take all of these problems together, when you look at the full scope of observations that don't quite fit our models, a pattern emerges. Something about our understanding of galaxy formation is incomplete. The question is, what? Let's start by examining the most straightforward explanation. Maybe we're just measuring things wrong. Distance measurements, mass estimates, rotation determinations, and environmental assessments all rely on complex observational techniques and analysis methods. Each measurement has uncertainties and potential systematic errors. Perhaps the early massive galaxies aren't actually as distant as we think. Perhaps our stellar mass estimates are inflated by incorrect assumptions about stellar populations. Perhaps we're misidentifying rotation directions or mischaracterizing environments. This is always the first hypothesis astronomers consider when observations don't match theory, and it's a healthy scientific instinct. Extraordinary claims require extraordinary evidence, and before you throw out your theoretical framework, you should make absolutely sure your observations are solid. In the case of the James Webb discoveries, the astronomical community has been appropriately cautious. Initial photometric redshifts, which are less reliable, have been followed up with spectroscopic confirmation whenever possible. Multiple independent teams have analyzed the same data and reached similar conclusions. Alternative explanations for the high redshifts, such as these being dusty, lower redshift galaxies whose light happens to mimic a high redshift spectrum, have been considered and largely ruled out. The distances are real. The early massive galaxies really do exist in the first few 100 million years after the Big Bang. For the rotation anomalies, decades of observations using different telescopes and techniques have confirmed that a substantial fraction of galaxies show misalignments between their spin and the local cosmic web structure. This isn't an artifact of one survey or one measurement method. It's a robust result that persists across different samples and different analysis approaches. For void galaxies and other location-based anomalies, the observations are similarly solid. We can map the three-dimensional distribution of galaxies through redshift surveys, and we can clearly identify which galaxies sit in underdense regions. There's no ambiguity about whether MCG plus 01-02-015 is in a void. It demonstrably is, surrounded by emptiness in all directions. So if the observations are reliable, the problem must lie with the theory. And here's where things get interesting. Because our current cosmological model, Lambda-CDM, is simultaneously one of the most successful scientific theories ever developed, and also increasingly showing signs of strain. Lambda-CDM successfully predicts the cosmic microwave background power spectrum, the large-scale distribution of galaxies, the abundance of galaxy clusters as a function of mass and redshift, the rate of expansion of the universe, and dozens of other cosmological observables. When Lambda-CDM makes a prediction and we go out and measure that quantity, the prediction is usually right to within a few percent. This is an extraordinary achievement, especially given that the model has only 6 free parameters. You'd be hard-pressed to find another area of science where a 6-parameter model explains such a wide range of phenomena so accurately. But Lambda-CDM is not without its problems, and these problems have been accumulating. There's the Hubble tension, where different methods of measuring the universe's expansion rate give answers that disagree by about 9%, far more than their stated uncertainties. There's the sigma-8 tension, where the amount of cosmic structure we observe doesn't quite match what the cosmic microwave background predicts should exist. There are tensions in measurements of the universe's age, tensions in the properties of the oldest stars compared to cosmological predictions, and now these tensions related to early galaxy formation. None of these individual tensions is necessarily fatal to Lambda-CDM. Each one might be resolved through better measurements, better understanding of systematic errors, or modest modifications to the model. But the fact that tensions keep appearing in different areas is causing some cosmologists to wonder whether we're seeing symptoms of a deeper problem. One popular proposed modification is early dark energy. In standard Lambda-CDM, dark energy is a cosmological constant, an energy density that remains constant as the universe expands. It dominates the universe's energy budget today, causing the accelerated expansion we observe, but it was negligible in the early universe. Early dark energy models propose that there was an additional energy component in the early universe, present for the first few 100 million years, and then disappearing or becoming negligible. This early dark energy would have affected the expansion rate during the epoch of first galaxy formation, potentially allowing structure to form faster than standard Lambda-CDM predicts. The appeal of early dark energy is that it can address multiple tensions simultaneously. It can help with the Hubble tension by changing the early expansion history in just the right way. It can affect structure formation in the early universe, potentially explaining the unexpectedly massive early galaxies Webb is finding. And it can be tuned to have minimal impact on late-time observables that Lambda-CDM already explains well. The problem with early dark energy is that it's ad hoc. There's no deep physical motivation for why such a field should exist. It's added to the model specifically to solve the problems we're seeing, rather than being predicted by some underlying theory. It also introduces additional free parameters, taking Lambda-CDM from 6 parameters to 8 or 9 depending on the specific model. More parameters mean more complexity and less predictive power. And even with early dark energy, you can't solve all the problems. Some versions that work well for the Hubble tension make galaxy formation problems worse, and vice versa. There's ongoing work to find a version of early dark energy that threads the needle, solving multiple problems without creating new ones, but it's not clear such a version exists. Another approach is to modify gravity itself. Einstein's general relativity has passed every experimental test we've thrown at it, but all of those tests are in relatively strong gravitational fields, like the solar system or binary pulsar systems. In the weak field limit relevant for cosmology and galaxy formation, modifications to general relativity are less tightly constrained. Modified gravity theories like MOND, which stands for Modified Newtonian Dynamics, propose that gravity behaves differently at very low accelerations than general relativity predicts. In the Mond framework, there's no dark matter. Instead, the apparent effects of dark matter are actually due to this modification of gravity. Mond is quite successful at explaining galaxy rotation curves, the relationship between galaxies' visible mass and their rotation speeds. It also naturally explains some of the scaling relations between galaxy properties that require fine-tuning in dark matter models. But Mond struggles with larger-scale phenomena like galaxy clusters and the cosmic microwave background, where dark matter models work very well. There are relativistic extensions of Mond that attempt to address these issues, but they introduce their own complications and haven't achieved the level of success that Lambda-CDM has. The fundamental challenge with modifying gravity is that general relativity is an extremely tightly constrained theory. Its mathematical structure is very rigid, and it's difficult to modify it in one regime without breaking predictions that already work well in other regimes. Most attempts to modify gravity end up either not solving the problems they were designed to solve, or creating new problems elsewhere, or both. A more radical possibility is that our understanding of the Big Bang itself needs revision. What if the universe didn't begin in a perfectly smooth, hot, dense state, as the standard model assumes? What if there were pre-existing structures or fluctuations that gave structure formation a head start? Some models propose a period of cosmic inflation before the hot Big Bang, during which quantum fluctuations were amplified to cosmic scales. These are the fluctuations that eventually grew into galaxies and clusters. Most inflationary models produce a fairly specific spectrum of fluctuations that matches observations quite well. But there are variants of inflation that could produce different spectra, perhaps with more power on small scales, which could accelerate early galaxy formation. Other, even more speculative ideas propose that the Big Bang wasn't the beginning, that there was something before it, perhaps a previous contracting phase of the universe, or a collision between higher dimensional structures called branes. If something existed before the Big Bang, perhaps it left imprints that affected structure formation in ways we haven't accounted for. These ideas are fascinating, but currently lack concrete predictions that can be tested against observations. They're more in the realm of theoretical exploration than established science. Setting aside modifications to the underlying cosmological model, perhaps the issue is with our understanding of the astrophysics of galaxy formation. Lambda-CDM tells us about dark matter and the large-scale structure of the universe, but it doesn't directly predict how gas turns into stars, how supermassive black holes affect their surroundings, how stellar feedback regulates star formation, or any of the messy baryonic physics that determines what galaxies actually look like. These processes are extraordinarily complex. Star formation involves turbulence, magnetic fields, radiation pressure, thermal instabilities, and chemistry, all operating on scales from individual stars to entire galaxies. We can't calculate star formation from first principles. We have to use simplified models, often called subgrid physics in simulations, that attempt to capture the average effects of these processes without resolving all the details. These subgrid models have free parameters that are typically tuned to match observed galaxy properties in the local universe. But what if the tuning that works for local galaxies doesn't work for early galaxies? What if star formation was genuinely more efficient in the early universe due to different gas conditions, different stellar populations, or feedback processes that operated differently? Some recent work has suggested that star formation in metal-poor gas, like what existed in the early universe, might be more efficient than previously thought. Observations of local low-metallicity dwarf galaxies show some evidence for this. If you take these hints and extrapolate to the even more extreme conditions of the first few 100 million years after the Big Bang, you might be able to increase star formation efficiency enough to build massive galaxies faster. But this is still a work in progress, and it's not clear it can fully account for what Webb is seeing. There's also the question of supermassive black holes. We now know that essentially every large galaxy contains a supermassive black hole at its center, with a mass typically about 0.1% of the galaxy's total stellar mass. These black holes are not passive passengers. When they accrete matter, they release enormous amounts of energy that can heat gas, drive winds, and regulate star formation throughout the galaxy. In the modern universe, this black hole feedback is thought to be a crucial part of galaxy evolution. But Webb has found supermassive black holes in the early universe that are far more massive than they should be given their host galaxy's properties. Some are nearly as massive as their entire host galaxy, rather than being a tiny fraction of it. This suggests that black holes and galaxies might have grown differently in the early universe, perhaps with black holes forming first and then gathering galaxies around them, rather than galaxies forming first and growing black holes at their centers. If supermassive black holes were more common and more massive in the early universe than we thought, their feedback could have affected galaxy formation in ways we haven't properly modeled. Perhaps their energy output actually helped galaxy formation by stirring gas and causing it to fragment, rather than hindering it. Or perhaps they affected the distribution of dark matter in galaxy centers, changing how efficiently gas could cool and form stars. These are active areas of research with no clear consensus yet. Another astrophysical wildcard is magnetic fields. We know magnetic fields exist throughout the universe, in galaxies, in the intergalactic medium, and even in the cosmic web itself. But the origin and evolution of these fields is poorly understood, and most cosmological simulations either ignore magnetic fields entirely or treat them as a minor perturbation. Recent observations have suggested that magnetic fields in galaxies and the intergalactic medium might be stronger and more widespread than previously thought. If magnetic fields were significant even in the early universe, they could have affected structure formation. Magnetic pressure can support gas against gravitational collapse, but magnetic tension can also help funnel gas along field lines, potentially enhancing accretion onto forming galaxies. The net effect depends on the field geometry and strength in ways that are difficult to predict without detailed simulations. Some recent simulations that include magnetic fields have found that they can indeed alter galaxy formation, sometimes speeding it up and sometimes slowing it down depending on the circumstances. This is promising but also frustrating, because it suggests magnetic fields are important, but we don't yet understand them well enough to make firm predictions. So, where does this leave us? We have a cosmological model, Lambda-CDM, that works extremely well for most things but is showing signs of stress when confronted with detailed observations of galaxy formation, especially in the early universe. We have various proposed modifications and extensions, from early dark energy to modified gravity to different assumptions about astrophysics, but none of them cleanly solves all the problems without creating new ones. This is actually a very exciting place to be scientifically. We're not in a situation where the theory is completely wrong and everything needs to be thrown out. Lambda-CDM is too successful for that. But we're also not in a situation where minor tweaks will fix everything. the problems are substantial enough that something genuinely new is needed. Historically, this is how scientific revolutions happen. A successful theory starts showing cracks. Anomalies accumulate. Proposed fixes become increasingly contrived. And eventually, someone comes along with a new idea that explains both the old successes and the new anomalies in a more elegant framework. We might be at the beginning of such a transition in cosmology. The observations from Webb are only a few years old. We're still in the phase of confirming them, expanding them, and making sure we understand them correctly. The theoretical community is actively exploring possible explanations. New ideas are being proposed and tested. Some will work, some won't, and hopefully out of this ferment will emerge a clearer picture. Looking forward, what comes next? Webb is still operating and will continue to observe for years, hopefully at least another decade. Every additional observation campaign has the potential to find more impossible galaxies, or conversely, to show that the early galaxies aren't quite as impossible as initial observations suggested. Follow-up studies that measure these galaxies' properties in more detail, their star formation rates, their chemical compositions, their dynamics, will help constrain theoretical models. The Euclid Space Telescope, launched in 2023, is conducting a massive survey of galaxies across cosmic history. It's designed primarily to study dark energy through gravitational lensing and galaxy clustering, but its data will also be invaluable for understanding galaxy evolution. Euclid will map the shapes and positions of billions of galaxies, providing statistical power that complements Webb's detailed studies of individual objects. Ground-based, extremely large telescopes coming online in the next few years, like the Extremely Large Telescope in Chile and the Giant Magellan Telescope, will have the resolution and sensitivity to study distant galaxies in unprecedented detail. They'll be able to resolve structures within early galaxies, measure their rotation curves, map their stellar populations, and generally provide a level of detail that's currently impossible. On the theory side, simulations are becoming more sophisticated, incorporating more physics and running at higher resolution. The next generation of cosmological simulations will include better treatments of star formation, black hole feedback, magnetic fields, and radiation transport. They'll be able to make more detailed predictions that can be compared directly to observations. This interplay between observation and theory is how science progresses. Observations reveal phenomena that theory can't explain. Theory suggests new observations that could test different ideas. Observers find those phenomena or don't, constraining the theory. Theorists refine their models and make new predictions. And gradually, understanding advances. It's important to emphasize that this isn't a crisis in the sense that cosmology is broken or that we don't understand anything. We understand an enormous amount. Lambda-CDM correctly predicts the large-scale structure of the universe, the cosmic microwave background, the abundance of light elements, the expansion history, and much more. Whatever modifications or extensions are needed, they'll have to preserve all of these successes while also explaining the new puzzles. That's a tight constraint, and it means the eventual solution, whatever it is, will be an extension or refinement of our current understanding, not a complete overthrow of it. But within that constraint, there's genuine uncertainty about what the answer will be. Maybe it's early dark energy or some other modification to the cosmological model. Maybe it's a more sophisticated understanding of star formation and feedback in the early universe. Maybe it's magnetic fields or some other astrophysical process we've underestimated. Maybe it's a combination of several things. Or maybe it's something no one has thought of yet. The galaxies exist. They're out there, shining in Webb's infrared detectors, rotating in unexpected directions, sitting in cosmic voids, clustering together in impossibly tight groups. The universe made them somehow, following the laws of physics, even if we don't yet fully understand how. Every impossible galaxy is a puzzle piece, a clue to some aspect of cosmology or astrophysics that we're not quite getting right. The fact that we've found so many puzzle pieces in just a few years of Webb observations is both humbling and exhilarating. Humbling because it reveals how much we still don't know. Exhilarating because it means there are discoveries waiting to be made, understanding waiting to be gained. This is why we build telescopes, why we map the universe, why we spend careers analyzing data and building models. Not because we already know the answers, but precisely because we don't. The universe is under no obligation to make sense to us, to follow the models we've constructed, or to form galaxies only where and when and how we think it should. It does what it does, following its own rules, and our job is to figure out what those rules are by carefully observing, measuring, thinking, and testing. So, when Webb looks back to the dawn of cosmic history and finds galaxies that shouldn't be there, galaxies too massive for their age, spinning the wrong way, living in impossible places, the correct response isn't despair that our models are wrong. It's excitement that the universe still has secrets to reveal, that there's still fundamental cosmology to be discovered, that we're privileged to live in an era where our telescopes are powerful enough to find these mysteries. A century ago, we didn't even know galaxies existed as separate structures beyond the Milky Way. 50 years ago, we had no idea what dark matter or dark energy were. 20 years ago, we'd never seen an exoplanet transit its star. 10 years ago, we'd never detected gravitational waves. The pace of discovery in cosmology and astronomy is breathtaking. Each generation of instruments revealing phenomena the previous generation never imagined. The impossible galaxies Webb is finding will eventually become possible. We'll figure out how they formed, why they're where they are, how they grew so massive so quickly. The answer will probably involve some new physics, some refined understanding, some piece of the puzzle we're currently missing. And when we find that answer, it will make perfect sense. We'll wonder why we didn't see it sooner. And then Webb or its successor will find something else that doesn't fit, and the process will begin again. That's the nature of science at the frontier. The map of knowledge has edges, and beyond those edges are territories labeled, "Here be dragons." The impossible galaxies are dragons, mysterious and wonderful, challenging our understanding and beckoning us forward. And just like the dragons on ancient maps, they'll eventually be explored, understood and incorporated into our cosmological framework. But they'll always remind us that the universe is stranger and more marvelous than we imagine, and that the quest to understand it is never truly complete.